So this week we're going to talk about complete ionic and net ionic equations and the difference between those. So there's really three types of chemical equations. Molecular equations are what we are accustomed to looking at. It's just our traditional balanced chemical equations. So there's a couple examples here. For example, we have ammonium sulfide reacting with potassium hydroxide, and then the products of that are ammonium hydroxide and potassium sulfide. And you'll notice that we applied our traditional balancing rules, so we had to balance out everything with these coefficients. And then to get these subscripts, that's based on the swap and drop rule for our charges of our ions or our polyatomic ions. And then lastly, the thing that's noted in here is the state of matter, AQ meaning aqueous, and then there's another example down here where S stands for solid, or this would be a precipitate. A lot of the times when we write these molecular equations, we leave those states of matter out, but for this particular lesson, it is important that you include that, and that you also know where to find the information to determine whether something is aqueous or solid. So as a refresher, aqueous, if you think back, meant for something to dissolve in water. Well, we've defined that, but what does that really mean? We've talked a little bit about dissociation. So aqueous substances, they dissociate into their ions when they are in water. And so if you're unsure whether or not something is aqueous, then you should check your solubility rules to determine if it's aqueous. And remember that term aqueous in terms of the solubility rules means soluble. So what it means to dissociate is if I have a substance, for example, K2S, which is the combination of two K pluses and an S2 minus ion. So if this is a compound, K2S, well, when this compound is in aqueous solution, it dissociates into its ion. It is no longer stuck together as K2S. We have K pluses and an S2 minus floating around. Or another example might be if I have the compound ammonium hydroxide, which is NH4 plus and OH minus, and since both of those have a +1 and a -1 charge, they stick together in a 1-to-1 ratio. When this thing is a compound out of solution, they can stick together, but in solution, it dissociates into its individual ions. So since it's a 1-to-1 ratio, I get one ion of NH4 plus and one ion of OH minus. And so there's a snippet of those solubility rules. That's what you're looking for. These are the ones we use in class. So soluble substances would be the ones that contain these unless they fall under these exceptions. Insoluble, meaning they do not dissolve in water, would be substances that contain these ions unless they fall under these exceptions. So that's your traditional balanced equation. Well, then there's a second type of equation where we start to get into showing more what the chemistry is that's happening. So for what's called a complete ionic equation, we take that balanced chemical equation, that molecular equation, and we take all of the aqueous substances and we break them apart into their ions, because all of these reactions, or most of the reactions that we deal with, are in fact happening in water. And so if something is aqueous, that means it dissociates into its ions in water. So we show that when we write a complete ionic equation. And then notice that gases, solids, and liquids are left unchanged. We do not break gases and solids and liquids into their ions. So here's an example. So going back to that molecular equation, that ammonium sulfide plus 2 moles of potassium hydroxide produces 2 moles of ammonium hydroxide and potassium sulfide. So that ammonium sulfide, this guy, is shown as being aqueous. And so what that means is we're going to write it as its ions. So this thing is made up of an ammonium ion, which is NH4 plus, and a sulfide ion, which is S2 minus. So we break that down into its individual ions. And if you recall, this 2 here is here because of the swap and drop method, because of the charge of the sulfide. That's the reason this is a 2. Well, because this 2 is here, that means that I have 2 ions of ammonium to make this compound electrically neutral, meaning the charge balances out. And so when I write my complete ionic equation, I have to also balance these ions. So if there's a 2 subscript here, because of swap and drop, I have to put a 2 coefficient on that ammonium to show that I have 2 ammoniums. The charge of ammonium ion is +1, so the subscript on this sulfide was a 1, which means I only need to represent 1 sulfide ion. So now let's look at this potassium hydroxide. If you remember, potassium is in group 1, so it's a +1 charge, and hydroxide is a -1 charge. And so when that breaks apart into its ions, we get a K+ and a hydroxide. We didn't have to put any subscripts down here because they're both +1 and -1 respectively. But when we balance this overall equation, this molecular equation, we did have a 2 here. And so what that means is if this KOH breaks apart into its ions, it's going to produce 2 potassiums and 2 hydroxides. And so we have to balance by including those coefficients in the complete ionic equation. Let's do the same thing for the product side. So ammonium hydroxide breaks into the ammonium ion and the hydroxide ion. Again, both of those are +1 and -1 respectively. But again, when we balanced the molecular equation, we had a 2 here. So taking that 2 and carrying it down to balance those ions, it's going to produce 2 NH4s and 2 OH minuses. And then lastly, we have the K2S. It breaks apart into K+ and S2-. And just like we looked at over here on the reactant side, this 2 subscript here is here because of the swap and drop we had to do, because of the 2- charge on that sulfide, which means it takes 2 potassium ions to balance out the charge of that 2- sulfur ion. So this final thing that we see down here with all these pluses and minuses, and it looks really, really complicated, this is a complete ionic equation where everything that is aqueous has been broken down into its individual ions, and then we checked for balance. Here's another example. So here we have sodium chloride, aqueous, plus silver nitrate, which is also aqueous, producing sodium nitrate, which is aqueous, and silver chloride, which is solid, which means it forms a precipitate. And all of these ions have ±1 charge. They don't have anything other than a ±1 charge on them. So the sodium chloride is going to break down into Na+ and Cl- because it's aqueous. Silver nitrate is going to break down to Ag+ and NO3-. Sodium nitrate is going to break to Na+ and NO3-. And then keep in mind, I said that we only break apart aqueous substances. We do not break apart anything that's solid, liquid, or gas. So because silver chloride is shown as being a solid, we leave it as a solid and we do not break it into its ions. So that's complete ionic equation. What about net ionic equations? In a net ionic equation, you may have noticed that in those previous slides, in a complete ionic equation, we had some things on the left side of the arrow and the right side of the arrow that were exactly the same. Those ions are called spectator ions. What that means is they did not do anything. They were floating in the solution before the reaction happened. They're floating in solution after the reaction happens, and they didn't do anything. In order for a chemical reaction to take place, something new has to be formed. If you start with something and you end with the same thing, then that's not a new substance. So we call them spectator ions because they just spectate. They don't do anything. In a net ionic equation, here's the big key. If you can identify a spectator ion, you cancel it out. Like you get rid of it. You just cross it out, and then you rewrite the equation with whatever is left. So let's look at one of those. Kind of going back to that very first example. So this first guy is what's our molecular equation, just our traditional equation where we balance it. The second guy is where we've taken all of those aqueous substances and split them into their individual ions. And I see that I have NH4 plus on both sides, so I can cancel that out because it's a spectator ion. I also have S2 minus on both sides, so I cancel it out. It's also a spectator ion. I have K plus on both sides and that hydroxide on both sides, so I cancel it out. So if we think about going back to when we were learning solubility rules, we said that if we do not form or precipitate, we call that no reaction. We have to have an insoluble product in order for us to say a reaction happens. Well, here, all of the spectator ions cancel out. This is the exact same thing. If all the spectator ions cancel out, we didn't make anything new. We just have a mixture of things that were floating around together before the reaction happened. They're floating around together after we mix them together, and so therefore no reaction. We didn't produce anything new. Let's look at this other example. So again, that first one was our molecular equation. Then we took it, we broke it into its individual ions for anything that was aqueous to give us our complete ionic equation. So let's check to see what kind of spectator ions we got going on. I see that I have Na plus on both sides, those cancel. I also have NO3 minus on both sides, those cancel. But that's the end of where I have ions that are exactly the same on both sides of this equation. On the left side here, I have Cl minus and Ag plus. On the right side, I have AgCl as a solid. That is not the same thing as Ag plus and Cl minus. So to get my net ionic equation, I just rewrite whatever's left, which in this case was Cl minus plus Ag plus, and that produced AgCl as a solid. That is your net ionic equation. So those are the three different forms of writing a chemical equation. The net ionic equation is useful because it really does show you what ions and what elements actually participated in producing something new. So again, you write your molecular equation, take anything that's aqueous, break it into its individual ions, and then any ions that are the exact same on the left side of the arrow as they are on the right side of the arrow, we cancel them out because they are spectator ions. If all of the ions cancel, then we say no reaction. If there are some things that are left, we rewrite anything that's left over, and that would be our net ionic equation.